Hello friends, welcome to EPG Pathshala. I am Dr. Ramasre Prasad from Department of Geography, Dr. Bhimrao Ambedkar College, University of Delhi, Delhi. Today I am going to explain ocean-atmosphere interaction, which comes under the paper Climatology. First of all, let us discuss what could be the learning outcome of this module. While going through this module, you will be able to identify the forces responsible for ocean-atmosphere interaction, analyze the operational aspects of these forces, discuss different atmospheric cells operating in different parts of the world, describe different type of motions in ocean waters, explain the causes of shifting of wind and pressure belts, analyze the role of moist winds and dry winds in ocean atmosphere interaction, and describe the role of warming and cooling of oceanic water. Now, let us start with introduction. The major driving force of ocean atmosphere interaction is solar heating. It is greatest near equator and keeps on declining towards poles. Ocean atmospheric circulation transports energy from higher received region to lower one. The resultant is the declining temperature gradient from equator to poles. Ocean and atmosphere are in constant exchange of heat, water and momentum. The interaction of the ocean and atmosphere adds rhythm in the structure of the world climates. The oceanic interaction transports moisture in atmosphere in the form of water vapor. Solar radiation is the ultimate driving force for all motions in the ocean and atmosphere and gives rise to the pronounced and regular diurnal and seasonal cycles throughout the world. Climate not only display repeating and regular cycles of solar radiation, but also displays variability that is not correlated with solar radiation. An attempt has been made to study the ocean and atmosphere interaction and its resultant outcomes in this module. Forces responsible for ocean atmosphere interaction. The motions of the earth with reference to sun are responsible for the generation of energy and its distribution in different parts of the earth. Earth's rotation results in causing day and night. The variation in the length of day results in the receipt of solar energy, its absorption and transmission. Earth's revolution results in causing the seasons and developing situations for the promotion of life forms. Tropics receive proportionately higher quantity of solar energy compared to temperate and polar areas. The transfer of energy takes place through radiation, convection and conduction. Now, let us discuss about the processes and factors responsible for ocean atmosphere interaction. There are several processes such as radiation, conduction and convection that are responsible for the transfer of energy from source. Similarly, energy transferred is subjected to several other processes that interfere and modify the impacts. In terms of factors such as winds, waves, currents and air are responsible for interaction between ocean and atmosphere. Medium of interaction. The energy received from the sun is in a systematic circulatory pattern. It is from sun to earth surface, that is land and water surface, from land and oceanic surface at atmosphere and return flow from the atmosphere to land and ocean surfaces. The cycle of interaction is augmented by processes such as radiation, conduction and convection. The energy so transferred is subjected to modification by the processes such as reflection, refraction and re-radiation. Air and the ocean are continuously exchanging heat. As the ocean has a higher heat capacity, it takes longer to adjust to changes in incoming radiation and therefore tends to change the temperature slower. This means that the surface of the sea is usually a different temperature at the air immediately above it, and heat is transferred between ocean and the atmosphere. Winds. The movement of wind from ocean to land is an important factor in transferring the moisture towards land areas. There is a marked difference between the response of a large land mass and oceanic surfaces to heat received from the sun. During summer, the wind over continents is much warmer and less dense compared to the oceans. Most of the solar energy received at the ground by the continent is confined to a thin layer of the earth. More and more solar energy received on the land surface is used in heating the nearby air parcel. On the other hand, solar energy is able to penetrate much greater depth of the oceans because of the steering. It is mostly operational under the action of winds. Consequently, a smaller part of the solar heat is available for heating the air. Apart from that, more and more evaporation is taking place from the ocean surface, with which a good amount of energy is carried away in the form of latent heat. The overall result is that the rise in temperature during summer is much less over the oceans than over the continents. Now, let us see about the salt and aerosols. Meteorologists are of the opinion that very large quantity of salt particles in the form of aerosols are injected into the atmosphere by the breaking up of sea waves. When waves strike the coastal region of the large land masses, they release a large volume of a spray. Millions of minute salt particles are injected into the free atmosphere in this manner, and they act as a storehouse of nuclei for condensation. Salt is continuously brought into the ocean by the rivers by draining off the continents. They carry minerals by dissolving from the rocks and run over and deposit the same in the ocean floor. Water evaporating or freezing at the ocean surface leaves the remaining water saltier, but rain which is not salty dilutes the salt concentration of the ocean. Now, coming to feedback mechanism. There are many feedback mechanisms between the oceans and the atmospheres. For example, evaporating water can condense in the atmosphere to form clouds. These reflect both incoming and outgoing radiation. It is because of this mechanism that cloudy nights are warmer than the clear ones. The system thus determines the temperature of the ocean surface. Surface air and air aloft are in opposite motion and thus form a cycle. It helps in transferring heat and other objects to upper surface. The most famous among such climate variations is the atmosphere's southern oscillation, which we call Walker circulation, which was put forward by Walker in 1924, and its oceanic counterpart, that is El Nino. Let us talk about Walker circulation. The interaction between oceanic water and atmospheric winds are closely related. Sir Gilbert Walker was the head of the Indian Meteorological Service during 1904 to 1921. Based on observation and experiments during the course of his assignment, Sir Gilbert Walker has developed a conceptual model of air circulation in the tropics in lower troposphere. According to the model, parcel of air follow a closed circulation in the zonal and vertical directions. Walker circulation is also known as Walker Cell. It is the result of a difference in surface air pressure and temperature over western and eastern Pacific Ocean. A pressure gradient from east to west causes surface air to form high pressure in eastern Pacific to low pressure in western Pacific. A line differentiating cold water layer with warm water layer is known as thermocline. The rising branch of Pacific cell of Walker circulation follows this warm pole which moves eastward. Sir Walker discovered a significant relation between monsoon rain over Indian Peninsula and South American pressure in April-May. He opined that overall effect of energy received from the sun was to set up impulses or natural oscillation in the atmosphere. Accordingly, eastern Pacific Ocean remains cooler with high air pressure. The surface winds blow in east-west direction, while winds aloft move in west-east direction, thus completing the circulation cycle. On the contrary, the western Pacific Ocean becomes cool and the air over the area is denser. A high pressure is created in the western Pacific Ocean. At the same time, the eastern Pacific becomes warmer and the air over the area is lighter, and hence a low pressure is result. Thus, the winds are west to east on the surface and east to west in the upper air motion. Such a situation is known as El Nino, which is responsible for a weak summer monsoon in northern hemisphere. Now, coming to the atmospheric cell in ocean atmosphere interaction. Because of rotation and differential heating of the surface of the earth, air motion takes the form of sails. The air motion of the sails on the ground is opposed to the air motion aloft as it completes the cycle. The operating sails from equator to pole are 3. A brief account of these sails and their role in ocean atmospheric interaction is well explained. It is named after George Hadley, which was invented by him in 1735. There is primary circulation cell known as Hadley Cell and 2 secondary circulation cells at higher latitudes known as Ferrel cell and polar cell. Hadley cell suggested that the distribution of solar heating would lead to rising motion in the equatorial regions and sinking motion near the poles. To compensate for the upper flow from the equator to pole, Hadley envisaged a return flow from pole to the equator at lower latitudes. It can consist from 30 to 40 degrees north and south and is mainly responsible for the weather in the equatorial regions of the world. The Hadley Cell is a tropical atmospheric circulation that features air rising near the equator, flowing poleward at 10 to 15 km above the surface, descending in the subtropics and then flowing equatorward near the surface. The circulation creates the trade wind, tropical rain belts and hurricanes, subtropical deserts and the jet streams. Now, coming to the Ferrel cell. William Ferrel in 1856 has pointed out the effect of Earth's rotation or the Coriolis force on large scale movement of air. Ferrel has pointed out that Hadley's model does not take into account the relative loss of heat from upper layer of the atmosphere. He has explained that towards higher latitudes, a loss of energy by long wave radiation exceeds incoming solar energy from the sun. The loss is equivalent to a cooling of the atmosphere by about 1 to 2 degree Celsius per day. There is then a middle cell between 30 degree north latitude to 60 degree north latitude, in which there are westerly winds at the Earth's surface and easterly winds aloft. This is known as Ferrel cell. The location of tropopause in the cell region is about 10 km above the surface. Now, coming to polar cell. Between 60 degree north and the pole, there lies a polar cell. The surface winds in this case are easterly and the upper winds are from a westerly direction. The polar tropopause is located at about 8 km above the surface. Thus, the effect of heating and convective currents is dominant in tropics, while cooling and subsiding currents dominates towards polar areas. Ferrel cell is significant as it balances the two opposite systems of the air circulation. Let us discuss about jet stream in ocean atmospheric interaction. These are narrow meandering upper air high speed winds. They play a decisive role in accelerating the dynamic situation that are conducive to transfer of energy and moisture to the atmosphere. A brief account of polar and subtropical jet is explained below. The jet stream operating in polar areas modify the weather conditions significantly because of lower altitude and velocity, that is about 130 km per hour. During a spring and summer season, polar jet transfers energy to atmosphere effectively. Popularly known as westerly jet, operate in subtropical and temperate regions. The normal speed of subtropical jet stream ranges between 160 to 190 km per hour. It significantly improves the weather conditions during winter and spring seasons in the region. The shift of subtropical jet results in improving the prospects of monsoon in tropics. Easterly jet. These winds operate in tropical zones at the speed of about 190 to 220 km per hour. Easterly jet operate over a relatively higher altitude and also cover a larger aerial extent as compared to subtropical and polar jets. They are significant in causing descent of easterly winds near subtropics during winter and southwesterly monsoon winds near intertropical convergence zone during summer. As a consequence, high pressure conditions develop in oceanic zones in tropics. It results in improving the status of southwest monsoon. Let us discuss about the Rosebury waves. In 1939, C.G. Rosebury, a Swedish meteorologist, suggested that upper easterly winds in the middle sail are wiped out by frictional drag and exerted by upper westerly winds to the north and south of the middle sail. There are many problems in the general circulation of atmosphere whose answers are yet to know. Rosebury waves are also known as planetary waves. They are caused by the Earth's rotation as a natural phenomena in atmosphere and oceans. Rosebury waves are the subset of inertial waves. On the Earth, these waves are giant meanders in the high altitude winds that exercise major influence on the weather. Now, let us discuss briefly about ocean waves and currents. Oscillating waves continuously transfer moisture and salt particles to the atmosphere. Similarly, ocean currents transfer water, heat and large quantities of marine biological products from equator to poles and poles to equator. In the process, ocean atmosphere maintain balance in the exchange of heat, energy and moisture. For example, ocean currents in Indian Ocean flow from west to east during summer, strengthening southwest summer monsoon. Thus, prospects of rain increase significantly during summer. On the contrary, ocean currents in Indian Ocean flow from east to west during winter season. Ocean currents in eastern coast of India coincide with the direction of northeast trade winds. As a consequence, Tamil Nadu region and its vicinity records sufficient rain during winter season, while it remains dry during summer season. Now, let us discuss about land and sea breezes. These are location specific bridge systems. They blow from sea to land during daytime as land area gets heated quickly due to solar radiation and develops low pressure. Sea surface on the contrary records high air pressure during the daytime because of its slow heating process. As a consequence, wind blow from sea to land and are known as sea breeze. During night, land area lose heat quickly and develops a high pressure, whereas sea surface remains comparatively warmer and thus develop a low air pressure. As a consequence, winds blow from land to sea during night and are known as land breeze. Now, coming to El Nino phases. Ocean atmosphere interaction is studied in terms of occurrence of El Nino and southern oscillation. The two concepts have been put together to be known as ENSO. There are two basic concepts related to ENSO phenomena. These are sea surface temperature, that is SST, and sea level pressure, that is SLP. The term El Nino refers to the extended episodes of anomalous warming of the ocean of the coast of Peru. The term southern oscillation refers to a sea level pressure swing between Darwin Island near Australia and the island of Tahiti in central tropical Pacific. Jerkins in 1969 recognized that El Nino and the southern oscillation, that is ENSO, are in fact just two different aspects of the same phenomenon. Ocean atmosphere interaction is at the heart of the ENSO phenomenon. An initial change in the ocean could affect the atmosphere in such a manner that the altered atmospheric conditions would in turn induce oceanic changes that reinforce the initial change. The atmosphere will respond by reducing the east-west gradient of SLP and consequently relaxing the strength of the easterly trade winds. The relaxation of the easterly winds in turn causes an eastward surge of warm water along the equator, positively reinforcing the initial warm SST anomalies. The positive ocean atmosphere feedback amplifies a small initial perturbations into large observable amplitudes. The satellite based observations have played an important role in understanding air-sea interaction and climate research, particularly in outgoing long wave radiations and SST. Space-borne microwave sensors have enabled all weather observations of SST, rainfall, surface wind and ocean surface height over the global ocean. With such a database, there has been rapid progress in understanding and simulating the climate and its variations. Jerkins, Menabes and Bryan were the first to work on ocean atmosphere general circulation model. Since then, occupied ocean atmosphere models are being used to work out interaction for ocean atmosphere circulation. Coming to El Nino and monsoon. The term El Nino refers to the extended episodes of anomalous warming of the ocean off the coast of Peru. On specific years, when the sea surface temperature in the equatorial eastern Pacific are anomalously warm, the east-west gradient in SST will be reduced. It results in the weakening of monsoon. The effect of El Nino on summer monsoon is significant. El Nino is a warm ocean current appearing along the coast of Peru. The appearance of El Nino reverts the condition of Peru current by developing warm water and moist air conditions over eastern Pacific and cold conditions in western Pacific. As a result, eastern Pacific along Peruvian coast in South America records high rainfall, while western Pacific along Australian and Indonesian coast record drought conditions. El Nino results in weakening of the monsoon, causing drought conditions and crop failure in monsoon regions of South and Southeast Asia. When Western Indian Ocean records low air pressure during winter and high air pressure during summer. It is said to be the positive phase of summer monsoon and sea surface conditions are normal. Heavy rains are caused in Indian subcontinent and neighboring regions during normal phase. Now, coming to the La Nina and monsoon relationship. La Nina, the word originates from Spanish meaning little girl. It is characterized by usually cold ocean temperatures in equatorial Pacific. During the period of La Nina, the sea surface temperature across equatorial eastern central Pacific Ocean becomes lower than normal by 3 to 5 degrees Celsius. It has extensive effect on the weather in North America, even affecting Atlantic hurricane. La Nina causes heavy rains over Malaysia and Philippines and Indonesia. Western side of the equatorial Pacific is characterized by warm, wet, low pressure weather as the collected moisture is dumped in the form of typhoons and thunderstorms. As a result of this motion, the surface water of Western Pacific coast is some 60 centimeters higher as compared to Eastern Pacific coast. Now, coming to the Southern oscillation phases. Southern oscillation is linked to low frequency temporal fluctuations in sea surface temperature in the equatorial Pacific Ocean. It is one of a number of manifestations of atmospheric fluctuations associated with alternating episodes of warm and cool sea surface temperature in the equatorial Pacific Ocean. Its impact are also experienced in Indian Ocean, where it influences the mechanism of monsoon. If air pressure along equatorial Pacific Ocean is higher than the air pressure in the Indian Ocean during winter, it is said to be a positive southern oscillation, indicating a favorable monsoon. When air pressure during winter is higher in Indian Ocean and lower in Pacific Ocean, it is known as negative southern oscillation. Such a situation results in a weakening of summer monsoon. The intensity of southern oscillations is worked out by the difference in sea level air pressure at Tahiti, which is situated at around 18 degree south and 149 degree west longitude. A station in mid Pacific and Port Darwin, which is situated at 12 degree south latitude and 130 degree east longitude, a representative station of Indian Ocean. A negative value of southern oscillation index implies low pressure over Peru coast and high pressure over Indian Ocean during winter season, explaining a poor monsoon phase. There seems to be a close correlation between the appearance of El Nino and the negative SOI. Southern oscillation has a period ranging between 2 to 7 years. Now, coming to the positive southern oscillation. It has been established that when sea level surface pressure is high over the Pacific, air pressure over Indian Ocean tends to be low. Since surface air pressure over oceans during winter season is inversely related to summer rainfall, prevalence of low air pressure over Indian Ocean during winter season is considered to be a sign of positive southern oscillations. The chance of favorable monsoon are generally linked with positive southern oscillations. Now, coming to the negative southern oscillation. The prevalence of high sea level pressure over Indian Ocean and low air pressure over Pacific Ocean during winters denotes the negative southern oscillations. It has been established that negative southern oscillation index is linked with a weak monsoon phase. Now, coming to the seasonal cycle, solar radiation is dominated by an annual cycle with a spatial structure that is roughly anti-symmetric near the equator. In response, the seasons in the northern hemisphere are opposite to those in the southern hemisphere. Over the oceans in the northern hemisphere, the seasonal maximum in SST generally takes place in September and March. Such a situation occurs after 3 months from summer and winter solstice. It is mainly due to a lag in large thermal inertia of the upper ocean. This local waxing and waning of solar radiation is a reliable predictor of season over most of the world except on the equator. The annual harmonic of solar radiation reaches a minimum near the equator. The same time, the pronounced annual cycle in SST is also observed in the Eastern Pacific and Atlantic Ocean. The climatological mean thermocline is shallow on both the locations. For example, the annual range of SST near the Galapagos Islands is about 6 degrees Celsius greater than most of the tropical oceans. It is to be noted that there is a westward co-propagation of seasonal SST and zonal wind anomalies along the equator in the Eastern Pacific. Significant increase from normal temperature in winters explains the occurrence of El Nino. Now, let us conclude this module. Solar heating is the basis for ocean atmosphere interaction. The motions of the earth with reference to sun are responsible for the generation of energy and its distribution in different parts of the earth. The earth's rotation results in causing day and night. The cycle of interaction is augmented by processes such as radiation, conduction and convection. The energy so transferred is subjected to modification by the process such as reflection, refraction and re-radiation. The variation in the length of day results in differential receipt of solar energy, its absorption and transmission. Earth's revolution results in causing the seasons and developing situations for the promotion of life forms. The insolation is greatest near equator and keeps on declining towards poles. Ocean atmospheric circulation transports energy towards poles. The result is the declining temperature gradient from equator to poles. Ocean and atmosphere are in constant exchange of heat, water and momentum. The interaction of the ocean and atmosphere adds rhythm in the structure of the world climates. The discussion ocean atmosphere interaction has enabled us to unlock the mystery of ENSO and other climate phenomena, leading to skillful predictions of ENSO, its global impacts and certain aspects of tropical atmospheric variability. The success of TOGA has proved a premise that a better understanding of ocean atmosphere interaction helps to improve model simulation along with an adequate observing system that leads eventually to useful climate prediction. Thank you very much.